So really, just thank you again to Professor Leong for the opportunity to share our work today, and we really hope it could start some conversations and some new connections. I'll start with some motivating examples from the literature. Narayan et al. In 2017 examined the role of coastal marsh in reducing floods and associated damages during Hurricane Sandy, which occurred in 2012. They modeled the eastern coast of the United States, and I'm showing just a close-up of New Jersey. The land cover was classified based on satellite imagery and assigned different values of Manning's N based on previous calibration studies. Marsh grass, which is shown here in green, was assigned a Manning's N of 0.04, and marsh with shrubs and trees was assigned a Manning's N of 0.1. Using a depth averaged flood model, they computed the maximum surge height. This was combined with information on land use to compute economic loss due to flooding. Scenarios were also run without marsh by reclassifying the marsh as open water by dropping the Manning's N to 0.02. The map colors indicate the percentage difference in those economic losses, which were as high as 138%. And the total cost difference was $625 million US. So I'll note that this study only considered the mean the mean water elevation, but of course, waves can also contribute to flooding. So in this scenario, we have a dike which is protecting the coast. And if we only consider the mean water elevation, which is in the red dashed line, we would not predict overtopping. But in fact, if we include the waves, the wave run-up can generate overtopping and flooding. And this is where the marshes are very valuable, because the marshes can dissipate wave energy and therefore reduce wave-associated overtopping. In another very fascinating study, Zhu et al. 2020 illustrated directly the influence of marsh on wave height and wave run-up. So in this aerial view of their field site in the Netherlands, you can see the dike or the seawall in gray, and then the marsh area is in green and the mudflat is in yellow. And the orange bars are denoting the maximum wave height during the storm event. At the edge of the marsh, it was 85 centimeters, but across the marsh, it was reduced to 37 centimeters. But if you look over to the right, where the marsh is narrower, there is larger wave heights at the dike, at the seawall of 73 centimeters. The reduction in wave energy also promoted deposition in the marsh, which is an added benefit for coastal stability. You can see that the bed level change, which is measured at these white triangles, there is erosion here at the edge, minus 23 millimeters, but inside the marsh, there was a gain of an accretion of sediment. So smaller waves at the seawall produced less run-up, and this plot summarizes two storms where the horizontal axis is the marsh width in front of the seawall, and the vertical axis is the wave run-up on the seawall. And the data show that within a given storm, wave run-up was reduced as marsh width increased. And again, note that the wave run-up far exceeded the mean water levels, which are shown with the horizontal dashed lines, which again highlights the important role of waves and wave reduction by the marsh. In the same study, they considered dike breaching, analyzing records from the 1717 Christmas flood. They show here the marsh width on the horizontal axis and the fraction of the dike length that was breached on the vertical axis. And the study found that a larger marsh width was associated with a smaller fraction of dike area breached. It is worth noting that marsh also provides other ecosystem services that have value, and this should be included in the cost-benefit analyses as well. These include habitat, sediment retention, water quality improvement, and carbon sequestration. The studies I've shared provide convincing evidence that that a marsh can dissipate wave energy and reduce flooding. However, the prediction of this benefit is not robust. Modelers still calibrate drag coefficients with in situ measurements at specific sites for specific storms, but we know that fitted drag coefficients are sensitive to plant morphology. That's one of the things I'm going to show today, and they cannot be used with confidence at new sites with different vegetation or even in different seasons at the same site. Today, I will share some physical models that describe drag on individual plants, which enable species-specific prediction of wave dissipation. After that, my colleague, Ernie Lee, will describe how he used the wave dissipation model in the context of a benefit-cost analysis to quantify the economic value of a marsh used in front of a seawall as part of a hybrid coastal protection. First of all, it's important to recognize that real plants are flexible and bend in response to current and waves. This is called reconfiguration. These images illustrate how a meadow of the seagrass Zostra marina folds over as the current magnitude increases. The reconfiguration reduces the drag, both because the frontal area is reduced and because the individual plants are more streamlined. In addition, by reconfiguring in this way, the meadow protects the bed from high velocity and high shear stress. As the plants bend over, more flow is directed over the top of the meadow and the velocity near the bed is reduced. Reconfiguration varies with plant morphology and rigidity, and this influences the drag. First, consider mangroves. The mangrove roots are rigid and do not reconfigure, such that the drag on a mangrove follows the classic quadratic drag law shown in this graph. F is the drag force. Specifically, the drag force varies linearly with velocity squared. To represent a mangrove in a hydrodynamic simulation, it would be reasonable to assign a constant drag coefficient or constant Manning's N that's not a function of velocity. Next, consider the marsh plant Spartina altiflora, which is highlighted here. Both the stem and the leaves are flexible, but to different degrees. So as the current increases, first the leaves reconfigure and then the stem. And as the plant bends in the direction of flow, it presents less frontal area and is more streamlined. And both of these effects reduce the drag on an individual plant relative to a rigid plant of the same morphology. If the stem and leaves were rigid and always stayed in the first posture, the drag would increase linearly with velocity squared, shown here in gray. But because of the reconfiguration, drag is reduced compared to the rigid posture. Importantly, this means that the typical drag coefficient formulation used in many simulations would have to be a function of velocity in order to capture this behavior. It's interesting to note that for some morphology, the drag actually increases with reconfiguration. Here is an example of a freshwater plant called Bacopa, which has stiff leaves and a flexible stem. When it's exposed to current, the stem bends, but the leaves do not, so that as a result, the drag increases faster than quadratic, shown with the red curve. To represent plants that reconfigure in hydrodynamic simulations, we need a more complex drag model than a fitted drag coefficient. That is, we need to predict the reconfiguration and its impact on drag. The influence of reconfiguration can be described in terms of two non-dimensional parameters. The first is the Cauchy number. The Cauchy number is the ratio of hydrodynamic drag to plant rigidity, and it describes whether or not a plant will bend. This graph shows the drag force measured on a live Spartina altiflora plant as a function of velocity in the channel, or velocity squared. So this is pictures taken in the lab. If the plant were rigid, the drag would follow the blue line. When the Cauchy number was less than 1, shown with the green shading, the plant did not reconfigure, and the hydrodynamic drag was not high enough to overcome the plant rigidity. For these conditions, the drag increased linearly with velocity squared. But when the Cauchy number was greater than 1, shown with the red or pink shading, the plant did reconfigure, reducing the drag relative to the rigid plant. With waves, the interaction between water and plant motion is more complex. Let's start by considering a single flexible element. This could represent a seagrass blade or a single marsh plant like a sedge. The plant moves in response to the wave. This dynamic reconfiguration can reduce drag relative to a rigid plant, primarily because the plant motion reduces the relative velocity. Notice that the tip of the plant moves with the water. The water motion is illustrated by the neutrally buoyant particles. But at the bed, where the shoot is rigid, there is relative motion between the plant and the water, and you can see eddies being generated associated with the flow past the stem. So you can see eddies, every wave cycle, you can see some eddies being shed. I won't discuss this today, but several researchers have observed that the turbulence shed by vegetation plays an important role in sediment resuspension and sediment transport. To understand how a plant reconfigures in waves, let's first consider the water motion. Beneath a wave, fluid undergoes an orbital motion showed with these dashed ovals, moving forward under the crest and backward under the trough. The radius of this orbit is called the wave excursion, which is shown in blue. It is proportional to the wave height, shown in red. The wave excursion has some control over how a plant moves. So in waves, the plant reconfiguration is controlled by both of these non-dimensional parameters. The first is the Cauchy number, which I already introduced, and the second is the parameter L, which I'll call the length ratio, which is the ratio of the plant length to the wave excursion. So if the Cauchy number is greater than 1 and the plant can move, there are two possible scenarios. The left-hand image shows the condition when L is less than 1, for which the wave excursion is large compared to the plant length. In this case, the plant only moves during part of the wave cycle and stops when it reaches its full extension. This means that the relative motion is only reduced during part of the wave cycle. The right-hand image shows the condition L greater than 1, for which the wave excursion is small compared to the plant length. In this case, the plant can move continuously, and the relative velocity and drag are reduced during the full wave cycle. This limit is relevant in most coastal systems. I won't show you the detailed derivation today, but the scale analysis predicts that the product of the Cauchy number times the length ratio, CAL, dictates how the plant moves and how that movement will impact drag. As the Cauchy number times the length ratio, CAL, increases, more of the plant moves passively with the wave, which decreases the total force relative to a rigid blade. So the photos show a plant in wave motion with increasing values of CAL from left to right. Above each photo, the horizontal blue line indicates the wave orbital diameter. At the smallest value of CAL, the leftmost photo, the plant does not move. In the next image, only the tip of the plant is moving, and the tip of motion of the plant is matching the wave orbital diameter. That is, there's no relative motion at the tip and thus no drag generated by the tip of the plant. If you go over to the rightmost photo, number 5, the full 1/3 of the upper portion of the plant is moving passively with the water and does not contribute drag. Here we varied CAL by changing both the wave height and the plant rigidity. but you can think of this progression as being associated really as just increasing wave height. Scale analysis shows that the ratio of drag on the flexible plant relative to a baseline drag on a rigid plant is proportional to CAL to the -1/4 power. This scaling gives us a way to account for plant flexibility relative to the baseline case of a rigid plant. This scaling was confirmed across multiple experiments. So the graph is showing the force measured on the flexible plant normalized the force on the rigid plant versus CAL, and the fitted line is indeed to the power of -1/4 within uncertainty. So far, we've only considered a single plant element, as shown as these images, and this can represent seagrass blades or sedges, but most marsh grasses have multiple leaves arranged around a central stem. We hypothesized that the force on a marsh grass can be modeled as the sum of forces on the central stem and on the multiple leaves, each of which will reconfigure. The stem and the leaves have different morphology and rigidity, but both obey the scaling law with CAL. So the rightmost term is the force on the stem, which is assumed to be cylindrical. For the rigid force is in the black font, and then the correction, the scaling, which accounts for reconfiguration, is in the red font, where Cauchy number and the length ratio are calculated for the stem. Similarly, we can make the force calculation for the individual leaves, which have a slightly different morphology and different rigidity. So the correction factor, CAL, must be calculated for the individual leaves. And then we can sum the force on N sub L leaves and the force on the stem. Experiments confirmed our prediction of force on individual plants. Live plants, here, this is Spartina altiflora, were mounted on a force transducer and exposed to waves. The image shows that both the stem and the leaves move under the waves, but the leaves move more because they are less rigid. The graph plots the force and the wave surface position versus wave phase. The blue line traces the water surface, that's the right-hand axis, and the left-hand axis and black lines show the measured and modeled forces, which have very good agreement. So now that we have a prediction of the force on the plant, we can use that to predict the wave dissipation. So the rate of wave energy decay is equal to the rate of work done against the canopy drag. So the rate of work is the force times the velocity, which we integrate over the wave period, T. So quickly, under the wave energy decay, rho is the fluid density, g is gravity, h is the wave height, cg is the group velocity. So its spatial decay is equal to the rate of work against the canopy drag, where ns is the number of stems per bed area, and the force is the force we defined in the previous slide, which includes the correction for plant rigidity. And the result is a prediction of wave height that can be made in incremental steps across the marsh. So the height at step I+1 is predicted from the height at step I, and the parameter CAL determined at step I. KV is the wave dissipation factor associated with the vegetated drag, and it can be incorporated with other factors influencing wave height, which is what Ernie will show shortly. We conducted several validations against field measurements at many different sites, but I'm only going to share one today. This is using data from Vuick et al. 2016, who measured wave height on a transect across two marshes at Helget and at Bath. Different species were dominant at each marsh. At Helget is dominated by Spartina anglica, and at Bath was dominated by Scirpus maritimus. Wave height was measured at multiple stations up to 50 meters from the marsh edge. And this plot of predicted versus measured wave height shows that the model did a good job predicting the wave evolution. And I emphasize that there was no calibration of drag coefficients. Having validated the model, we can use it to explore the impact or morphology and understand some general trends that should be considered when modeling marshes. In this example, we are considering the contribution from leaves. So we compared the drag generated per marsh area for plants of different morphology, which are associated with different amounts of biomass per bed area, which is shown on the bottom axis. So biomass per bed area is a common ecological parameter that is monitored in marshes. We're going to contrast the bulrush, shown in red, which has no leaves, and the cordgrass, shown in blue, which has many leaves. The cordgrass has 1/8 the biomass. So the cordgrass, shown with the blue dot, has 1/8 of the biomass compared to the bulrush, shown with the red dot, but it produces a comparable drag. This is because the leaves have a high surface area per biomass. I'm making this point because most coastal models represent marsh plants only by the stem, not the leaves, and the physics that is lost by excluding the leaves must be absorbed into the calibrated drag coefficient. But now we have a better understanding of how the leaves contribute, and we can incorporate that into a more physically robust model. This slide illustrates how marsh width and water depth influence wave attenuation. Starting with an offshore wave height of 1.5 meters, we predicted the wave height at the marsh inland edge, shown on the vertical axis, as a function of marsh width, shown as the horizontal axis, and the plant height was 1.3 meters. First, note the non-linear relationship between wave height and marsh width. Drag, and thus wave dissipation, are both a function of wave velocity, which scales with wave height. As a result, the rate of wave attenuation is highest when the wave is largest, that is, at the seaward edge of the marsh. This is why the marginal benefit of the marsh decreases as the marsh width increases. As the waves get smaller over the marsh, the additional marsh attenuation generated by adding more marsh decreases. And this marginal benefit aspect is going to be reflected in the benefit cost analysis that Ernie will discuss shortly. Second, as wave depth increases from blue to red to yellow, the wave height at the marsh inland edge also increases. And this is because, obviously, as depth increases, the vegetation occupies a smaller fraction of the water column and is influencing a smaller fraction of the wave motion, and therefore has a weaker influence on wave attenuation. It's important to note this significant role of water depth in setting wave dissipation, because this influence is not directly captured simply by assigning a bed friction coefficient factor in a depth average model. So you have to account for water depth also. Finally, the morphologically sensitive drag model provides a way to compare the wave dissipation potential for different plant species, which might be useful when contrasting different sites. This graph depicts the additional wave attenuation by 40 meters of marsh relative to the same distance with no marsh vegetation. Stiffer plants provide greater wave dissipation. So the horizontal axis is the product of the modulus of the stem and the bending moment of inertia, so which EI referred to as rigidity. In particular, notice that the larger and stiffer Phragmites, which is shown with the blue dot, produce the strongest wave attenuation. And this is despite the fact that it grows at the smallest area density, 340 plants per meter squared. In many regions, including the US, Phragmites is considered invasive, and it's often undesirable for ecological reasons as it outcompetes native species. but its wave attenuation performance may make it desirable at some sites. Let's contrast it with Scirpus mariceter, which is shown with the yellow dot. This provides the least wave attenuation due to its low stiffness. And this is despite the fact that it grows at the highest stem density at 2,400 shoots per meter squared. So I note this because in many numerical simulations, plants are represented just by stem density and diameter. So I will acknowledge that the two species we're contrasting also have different diameter, but they ignore the rigidity, which also plays an important role in the difference between species. Finally, for two of the species, we included both the live and dormant or winter states of the plant. For example, consider Spartina anglica, shown with the orange points. The live state or healthy state, which is the circle, is stiffer and offers significantly more wave dissipation benefit compared to the dormant state. This highlights the need for more field observations to characterize the variation in plant characteristics over the seasonal growth cycle. In particular, most ecological data that's available is done at the peak growth point, which is the greatest benefit you'll get for wave dissipation. We really need to have more measurements done when the benefit of the marsh is at its weakest, which is during the winter phase. I hope that I've been able to relay the importance of plant morphology and rigidity in describing wave dissipation by a marsh. In the next part of the talk, Ernie Lee will use the new wave dissipation model to quantify the value of marsh within a benefit cost analysis.
Thank you. So benefit cost analysis is an economic framework, and we are trying to see if the marsh fronted seawall is economically justified. So here, I consider three benefits. The first one is the avoided seawall height, because you can have a shorter seawall to deliver the same amount of coastal protection. Second is the environmental services that the marshes provide. And thirdly is the reduced erosion, which is not quantified at the moment because the volume of erosion is pretty hard to estimate. In terms of cost, there are two. First is to plant the marshes, and second is to establish this marsh creation and stabilize it so that the marshland can survive. This benefit cost analysis is measured with a metric of the benefit cost ratio, which is simply dividing the monetary money benefits divided by the money invested for this construction. And so for a benefit cost ratio of above 1, it means that there's more benefits than cost. Here is a schematic of a case without vegetation. Freeboard is the distance between the water level to the top of the seawall. And with a known freeboard, we can get an overtopping rate, which is the rate of volume of water going over the seawall. In the scenario with vegetation, and if we want to have the same level of coastal protection, we would have the same overtopping rate. And this will give us a freeboard with the consideration of vegetation drag. And because vegetation drag produces wave attenuation, and so the waves at the seawall are smaller. As a result, you don't need as much of a seawall. This translates into a savings of seawall heightening, and it can be computed using the Eurotalk 2018 manual. And specifically, this can translate into the monetary cost savings for reaching the same coastal protection value. Marshes are also important for the environmental services. The wave attenuation favors marine habitat because it has a reduced wave intensity and flow velocity within the field, so that younger or smaller plants can, smaller marine habitat can survive. Marshes also provide benefits in water quality, aesthetics for the environment, as well as carbon sequestration, favoring this deposition of sediments. These benefits can be monetized, and they are monetized in some of these lookup tables tabulated by government agencies such as FEMA in the US, as well as some literature also reported the environmental service benefits in monetary terms. And we have collected all these numbers and categorized into low, medium, high categories to see how sensitive are using different values of environmental services are into what the benefit cost ratio output would be. In terms of costs, there are two. The first cost is to plant the marsh, and then the second cost is to make the marshland so that the marsh can survive. And these are values that we tabulated from literature collected in the US as well as globally. What are the costs of constructing such a marshland? In economic analysis, we have to standardize all the values so that they represent the same units. In the first two among the benefits and cost items, some of them are present value, which are some first cost investment. Imagine if you are building a marsh, you invest a certain money, but the marsh lives for 100 years. And so you have to normalize it so that everything is in the same units of annualized value. And this is done by using interest rate to account for spreading that cost or benefit into annualized value, such that the benefit cost ratios are computed for every year. Here we're considering the marsh area serves for 100 years, compounded annually. The interest rates we're looking at were tested from 0 to 11%. This range of percentage covers what was used in the US, for example, which is 2.25 to almost 9%. In Europe, they also use a very similar range of percentages, and some literature reported that the natural assets should be applied to about 0 to 11% for applications for land use planning, which is like this marsh fronted seawall. So here's a schematic of a marsh fronted seawall where I would present some of the sensitivity analysis. Just to go over the diagram, we have waves coming from the left going to the right. There's a water depth of small h, and the wave height at the seawall is denoted as capital H. And we have vegetation width right in front of the seawall, providing that vegetation drag. So with this schematic, we played with different values of that input to see how sensitive they are on the benefit cost ratio. Here, the first one I'm showing is the variability in water depth. We're testing for water depths of 2 meters, 3 meters, and 4 meters. This is the same scenario that Heidi have shown with vegetation of 1.3 meters tall. And the x-axis of here is we have vegetation width. Y-axis is the benefit cost ratio. As mentioned by Heidi, that the marshes provide a marginal, a decreasing marginal benefit as you increase the vegetation width, because as you have more width, the gain in wave attenuation reduces for every incremental increase of vegetation drag. And this is shown by the decaying shape of benefit cost ratios from 0 vegetation to 100. More importantly, we note that for all the cases, they have benefit cost ratios above 1, which means that there's more benefit than cost, regardless of the water depths we tested. I also wanted to note that near the higher edge of more vegetation, all three curves converge to a same value because of this diminishing returns of what the vegetation drag provides, as that's how much wave attenuation you can get. And at the higher, longer widths, it's dominated by the environmental service benefits that the marshes provide. Next, we look at the sensitivity of this benefit cost ratio in terms of what discount rate do you choose to use, because different government agencies choose their own discount rates to consider whether a project is beneficial or not. Here, looking at the ranges from 0 to 11, we show that a very similar curve of decaying on each of the curves, But if you look at the magnitudes of the benefit cost ratios, they vary by about 50% if you choose a 0% versus 11%. And this significantly shows that the choice of discount rate would significantly affect the magnitude of benefit cost ratio for policy decisions, as I will show with a real life example later how that would play out. The third sensitivity analysis is we tested with different marsh species because Heidi mentioned about Phragmites being a very stiff plant versus Scriptus marquiter. It's a more flexible plant. And shown on the on the left figure, we have the blue curve with significantly more benefit cost ratio than Scriptus. Seasonality also plays a role because the flexibility depends on whether it's in its healthy state or dormant state. And this is also reflected with a 50% difference across. So we show that the benefit cost ratio is also a temporally sensitive to the seasonality. And more clearly, plotting against x-axis, we have the stem rigidity, which is the product of the Young's modulus to the second moment area. Looking at 40 meters of vegetation, which is pretty short, and it's where we see it in urban areas, we show that the benefit cost ratios can span from 4.5 to 3 with a four order change in stem rigidity. And so this is how marsh species influence benefit cost ratio. And to put it in more context, this is a real life example of Juniper Cove. It's located in the east coast of United States. Specifically, it is north of Boston. And here is this view of the site where the waves travel from right to left. At Juniper Cove, there is a breakwater. And after the breakwater, we see on the northwest side, there's a 79-meter seawall, and there are salt marshes fronted of it. So the question we wanted to ask is, how important are the salt marshes in front of the seawall? And is it economically justified to restore the salt marshes to protect compared to heightening the seawall for this location? This is how it looks like in field pictures taken by myself, showing how high tide and low tide compare. As you can see, at low tide, it exposes a lot of the vegetation. And more importantly, the seawall at the site is about a meter, which is not very tall. And you see there's a car on the right-hand side photo showing for scale of how short the seawall is. And this can give some insight whether it's worthwhile to increase the seawall or we want to protect the marshland so that we can maintain the same seawall for the same protection level. So I've conducted a one-dimensional wave modeling, and the wave model starts at the breakwater. I've drawn 10 transects where each transect has there are 3 different return periods of wave conditions that I simulated, which are 10-year, 50-year, and 100-year storm events. And at each of the transects, I march every meter from the breakwater to the seawall and considered 4 different effects that would influence wave height. Firstly is the vegetation drag. Second is shoaling due to the change in bathymetry. Thirdly is the wave breaking. Mostly is the depth-induced wave breaking. And lastly, it's bed friction. The product of each of these multiplied by the previous previous spatial step wave height will give me the wave height at the next step. And so I do this for every meter. This is an engineering drawing from one of the projects. They are planning to see whether it's worthwhile to heighten the seawall or extend the marsh area. The red area shaded is where Spartina patens will be planted, and the green area is where Spartina alterniforme will be planted. By overlaying the 10 transects, we see that each transect will have their own bathymetry, as well as individual distribution of where the plants are, and also what kind of species. So in my model, because I compute the wave height every meter, I can substitute the specific plant morphology and characteristics at each of the time step, knowing perfect information of what the ground profile looks like. So looking at some of the results, looking at the 10-year and 100-year storm events, I denote circles for healthy plants, triangles for dormant plants, and crosses for cases without vegetation. By comparing, you can see that the crosses and the circles are very far apart, showing that having healthy vegetation is very important. And here on the x-axis, I'm showing the transect number, which are the wave directions that I simulated shown on the previous plot. And because they have different bathymetries, the effect of wave height, the magnitude of these wave height at the wall are very different. Now also look at the circles and the triangles showing the different seasonalities of the vegetation. It also shows a significant difference. So it is important to account for the seasonal variation, and this can be done by measuring the stem rigidity change throughout the season, which is not able to do if you calibrate it at a specific season, because that calibrated number that only represents the state of the vegetation at a specific point. But in our implementation, because we are using the plant-specific parameters in a specific season, so we can capture the difference between the triangle and the circle. Now, the wave height at the seawall can translate into the wave overtopping at the seawall, as shown here. And for comparison, the green shaded area is where it's safe for pedestrian safety. And you can see that for the circles, you need the circles in order to satisfy the pedestrian safety level, because only the circle points are below the green shaded area. The purple line is shaded for road traffic safety, which is where fire trucks or ambulance emergency vehicles need in order for them to safely drive through. And you can see that only cases with vegetation would satisfy these safety requirements. Lastly, we look at how each of these translate into benefit cost ratios. The circle points show healthy vegetation, and so the x-axis is a discount rate. So for healthy vegetation, for 100-year and 10-year storm, they both have benefit cost ratios above 1 at all discount rates. But if you consider the dormant ones, the benefit cost ratio is only above 1 if you have a discount rate of 5. And so if a governor decides to have a discount rate of below 5, it would favor the project to implement this marsh restoration. But if they choose a very high discount rate, it would significantly change its decision of whether it's worthwhile to do the marsh restoration. So to conclude and a little bit highlight on what I'm currently working on, a lot of these models require smart specific characteristics, specifically plant height. And a lot of these plant heights are measured in the field with a meter stick or whatever direct means, but you need to physically go there, and it's very labor intensive. So to make it more efficient, I'm developing a method to use drone imagery and reconstruct the digital elevation model such that we can estimate the canopy height. And these are pictures in the field. And with that, for every plant height, we measure the bending rigidity of the stem on the 3-point bending and get its frontal area. By doing so, I can construct these allometric relationships where for a given known height, I can get the bending rigidity and frontal area and all the other parameters I need in the wave modeling so that I can plug them into implementation for characterizing the wave attenuation specifically for that plant species, as well as accounting for seasonality. So to summarize, our findings can be found in more detail in the paper on the left. You can scan that QR code, as well as a more easily understood language published in MIT News on the right-hand side. So that's the end of our presentation, and we're open for questions.